with the
Well, let me just say, first of all, thank you for joining us from the University of Oslo. And I know you've got some other things scheduled today, so we appreciate you making the time and answering the queries of a random graduate student you met in Spain. But yeah, much appreciated. And thanks for joining us. We look forward to your talk.
Okay, thanks a lot. Yes, great to be here. This is also work in progress, and I'm very much from the philosophy of mathematics side. So I am very interested in hearing what the Aristotle scholars here think about this. So concepts of infinity. So let me begin then just by kind of laying out the two notions of infinity that I will be using, two to begin with at least. So there's a contemporary notion of infinity where we say that a collection is infinite if it's too large to be counted by any natural number. So when I use the word infinite, I will always use it in that contemporary sense, just to avoid confusion. And on this notion of infinity, you may kind of think of infinity as the property of being off the scale of natural numbers. So no natural number is big enough to indicate how large that collection is. And then there is the Aristotelian notion of infinity, apeiron. Here I will use the Greek term apeiron just to avoid conflation with the contemporary notion. And this is, of course, what's unbounded or unlimited. And a nice characterization of infinity, as Aristotle thinks of it, is from the Physics again, where he writes that something is infinite if, taking it quantity by quantity, we can always take something outside. Okay, so here you may say that apeiron is a property of being off the scale again, but this time off the scale of quantities, whatever exactly the quantities are. Right, since you can try to exhaust it taking quantity by quantity, and there's always something outside when something is apeiron. Right, so apeiron is to be off the scale of quantities. And then the question that immediately arises is, how are these two notions of infinity related? And this will depend then on how the quantities that Aristotle talks about relate to the natural numbers. So suppose the quantities actually correspond to natural numbers. Well, then you get something interesting, namely that the two concepts of infinity are at least extensionally equivalent if the quantities are finite and they're all finite. Okay, then Aristotle has many arguments, several arguments against completed infinities or completed apeiron, as I will put it. Zeno's paradoxes were mentioned, problems concerning the divisibility of the continua figure here. I will not today say anything about any of these arguments. I will focus on what I think of as a conceptual argument for the same conclusion that there can be no completed apeiron. So here's the argument I have in mind. Physics 3.6 again. So you start off with the definition of infinity that I just gave you on the previous slide, that something is infinite if, taking it quantity by quantity, you can always take something outside. So infinity is being inexhaustible by quantities. Okay, and then next, on the other hand, what has nothing outside is complete and whole. For thus we define the whole, that from which nothing is wanting, as a whole man or a whole box. On the other hand, that from which something is absent and outside, however small that may be, is not all. And then finally, whole and complete are either quite identical or closely akin. Okay, so here you have the idea that substances like a whole man and a whole box or a whole of any sort is exhausted. There's nothing outside. And then you get the conclusion that nothing is complete, which has no end. So nothing is complete and infinite, endless. Okay, so here's how I understand the argument, how I analyze it, and what I think of it. So it seems to me that this is a very interesting argument, and the conclusion does follow analytically from the premises. I think he's right about that. So if we accept Aristotle's definitions, that's a big if. But if we do, then the argument does go through. So a pairon, after all, is defined as what can't be exhausted by any quantity. Something completed or whole is, by definition, what is exhausted by a quantity, namely itself, that thing. So then there can't be any completed apeiron. That would be like a completed, incompletable thing, and that's just impossible. So the interesting question here, as I see it, is really whether the definitions are defensible or not. So that's a question to which I will return quite soon. First, though, I wanted to just say a little bit about Aristotle's notion of apeiron and how apeiron exists, so the mode of existence here. And on that question, I find this passage very useful. So you start off here with characterizing infinity again. So for generally the infinite has this mode of existence. One thing is always being taken after another, and each thing that is taken is always finite, but always different. So this idea of always being able to go on, take another thing of the irrelevant sort. Okay, that's a background. And now we get to the substance. So being has more than one sense, so that we must not regard the infinite as a substance, I guess we may say, such as a man or a horse, but must suppose it to exist in the sense in which we speak of the day or the games as existing things whose being has not come to them like that of a substance, but consists in a process of coming to be or passing away. Definite, if you like, at each stage, yet always different. Okay, so what's going on here, as I understand it, is that apeiron has this special mode of existence, not like a substance, which is complete, and the infinite is the incompletable, so it couldn't be that mode of existence. Rather, its mode of existence is like that of a substance, like something that is coming to be and passing away. And processes can be incompletable, like, for instance, the process of taking a line and forever bisecting it. That's an incompletable process. So that's, and also apeiron, of course. So that is a kind of mode of existence that infinity requires, according to Aristotle. So back then to this conceptual question of whether Aristotle's definitions are acceptable, whether we should accept these. So here it is natural to worry that the concept of apeiron is very demanding, perhaps too demanding. This was certainly my worry when I started to think seriously about this. So remember, apeiron is what can't be exhausted by any quantity. But what if quantities are really abundant? What is if there are lots and lots of quantities? Then nothing would have that property of being inexhaustible by quantities. So it is a very demanding concept, and it is natural to worry that the concept of apeiron might not even be instantiated. And if so, then sure, we had that interesting argument that nothing that is apeiron could be completed. That's fine. But if nothing is apeiron to begin with, then of course, a fortiori, nothing that's apeiron can be completed. That's uninteresting if the concept isn't even instantiated. So this becomes an issue. And let me give a response to that. We'll get to an Aristotelian response shortly, but now I'll first kind of use what we now know to comment a bit on why Aristotle felt so certain that, yeah, of course, the concept of apeiron is instantiated. And the response I have in mind here is that Aristotle implicitly relies on what we see as the Euclidean conception of part or quantity. And with this conception, you have the Archimedean principle. So quantities being finitely comparable. So for any two quantities, x and y, say, there's some natural number n, such that you can take n copies of one quantity and in that way exceed the other quantity in magnitude. Right, that's being assumed. That's one of Euclid's common notions and part of what was being assumed here. And this entails then that every quantity is finite. Okay, so that's a background assumption. And given that view of quantities, then Aristotle's concept of a pairon is extensionally equivalent to our concept of infinity. Right, so our concept of infinity, as I defined it, following the usual definitions, is being too large to be measured by a natural number, by a finite number. And Aristotle's notion of infinity is too large to be measured by any quantity, but the quantities are finite. So these two notions are extensionally equivalent. So then Aristotle should be as convinced that a pairon is instantiated as we are that infinity in our sense is instantiated. So say the natural number line, that would be an example. So the revised challenge here is fine. This all follows when you use this Euclidean conception of part or quantity. But why accept that conception? Right, so we have other conceptions available now. So we're not forced to accept that Euclidean conception. So now I'll start to move into definitely kind of post-Aristotelian territory. First, Galileo's paradox, then Cantor. What Galileo's paradox is the conflict when you go to the infinite between these two principles. So first, this Euclidean principle that every whole is larger than any of its proper parts. That's one of Euclid's common notions. And it's very natural when you think about it. And then you have the so-called bijection principle, which says that the number of any collection is preserved under any one-to-one correspondence, or bijection, as we call these. So you have my left-hand fingers, my right-hand fingers, these can be bijected. Okay, so they're in one-to-one correspondence. So by this principle, it follows that the number of these is identical with the number of those. Okay. And then as Galileo realized very clearly, if infinite collections are possible, then these two principles come into conflict. They clash. So one natural conclusion to draw is that you can't have infinite collections. Or at least infinite collections can't be wholes. So you get back to the kind of view we had on the previous slide, that this Euclidean conception of quantities, that they are all finite. That's a conclusion you may take away from Galileo's paradox. Okay, so that would shore up the Aristotelian way of doing it. But here comes Cantor and the Cantorian revolution. So as you know, probably, Cantor's response was to just reject Euclid's principle, the idea that the whole has got to be larger than its proper parts. That's true when you look at the finite, which is where our intuitions have been formed, but it's not true in general, Cantor says. So you should reject the Euclidean principle and retain the bijection principle. Okay, so when you talk about quantity or number in general, really that should all be based on the bijection principle. Okay, so this gives rise to a very rich and nice mathematics of the transfinite. So the centerpiece of that mathematics is Cantor's theorem. The idea then that for every set, whether finite or not, there are more subsets than members. So that's a very powerful way of going from a large collection, maybe so large that it's infinite, to an even larger collection, namely the collection of all the subsets of the first collection. So it's a super powerful way of increasing size or increasing number cardinality. And the result then is that we get what Cantor calls the extended number line. So we had with Aristotle and pre-Cantorian mathematics, the ordinary number line of all the natural numbers. And with Cantor, you get extended numbers. So you get Aleph 0, Aleph 1, infinite numbers. And there too, there is an unbounded sequence of these transfinite or infinite numbers, which become available when you do what Cantor recommends doing here. Okay, so the number line extends. There are more quantities than we had first realized. That's the take-home lesson here. So here's how I think of it kind of pictorially, that we talk about the number line. Okay, what's on the number line? We used to have kind of a small number line with all the natural numbers on it, and that was it. With Cantor, we get this huge number line with not only the finite numbers on it, but transfinite numbers on it as new and much larger quantities. So the number line increases. There are many more quantities than we had antecedently realized. And then something very interesting happens to the idea of being so numerous, so many that you're off the line of quantities, off the scale of quantities. That splits, of course. So what is it to be off the number line, so numerous that no number suffices to specify how large? Well, one way of taking it is that you're off this original little number line. You're off the scale of natural numbers. That's little omega in Cantorian notation, or infinity in the contemporary parlance as I defined it and have been using it throughout this talk. And then the other sense in which one may be off the scale of numbers is that you're off the scale of numbers altogether. Not just the scale of natural numbers, but off the scale of natural and transfinite numbers. Okay, we're off this scale. So this has a sign too in Cantorian mathematics, big omega, and known as absolute infinity. Okay, so infinity splits into these two notions. And then there will be three substantive claims that I will make and defend here. The first of these substantive claims is that apeiron, the Aristotelian notion, is really closer to absolute infinity than to our notion of infinity. And why is that? Well, apeiron is being off the scale of quantities, loosely speaking, and the scale of quantities now has new extended quantities, the transfinite numbers. So in intention, the concept of apeiron is closer to that of absolute infinity. And then it just so happens that Aristotle had a view of what are the quantities. And when you plug in that view, then the Aristotelian notion of apeiron is extensionally equivalent to our notion of infinity. But the intention is closer to this one. That's my claim. So on then to why we need the concept of apeiron. So you may have thought that, fine, with Cantor, things change so dramatically. You now have the notion of infinity, little omega, and you have the notion of big omega or absolute infinity. Isn't that enough? Can't we just stop using this Aristotelian talk altogether and just move on? That's a natural thought, and many people wish to just move on. So here I would like to look at Aristotle's argument why the notion of apeiron is needed. And then on the next slide, I'm going to give a kind of updated, modernized version of this argument, which I'm very attracted to myself. I would even go so far as to defend that modernized version. So, but Aristotle first. Number, on the other hand, is a plurality of ones and a certain quantity of them. So the idea here, as I understand it, is that number is kind of a property of a big plurality of units or ones. Okay, that's what number is. And then B, in the direction of largeness, it's always possible to think of a larger number. For the number of times the magnitude can be bisected is infinite. So when you have a big plurality here, you can always go to a yet bigger plurality just by adding one, by bisecting one of the objects you have. Okay, so for every plurality, it's possible to think of an even bigger plurality, which then instantiates a larger number. And then you get the distinctively Aristotelian potentialist view of infinity coming out of this. So hence this infinite is potential, never actual. The number of parts that can be taken always surpasses any assigned number. But this number is not separable from the process of bisection. So the number, when you say that something is infinite, that number is not ascribed to something that can be separable from a process, say that of bisection. So it's not that you have a big plurality of things, say, separable from the process by which that plurality was formed. And then you say that, these things are infinite. Because if so, then you could go beyond, add one more thing. So number then is not separable from the process of bisection, and its infinity is not a permanent actuality, but consists in a process of coming to be, like time and the number of time. So as I see it here, the idea is that the natural number line, all of the quantities Aristotle thought existed, is apeiron, because it's not a quantity or plurality of ones. Because if so, it would be bounded. It would be something you could transcend, something you could go beyond. Rather, apeiron is more akin to a process. So we need this notion. And here's then the modernized version of it. So why apeiron is needed even after contour? So this is claims that are starting to be, or actually somewhat controversial in the philosophy of mathematics, just to announce that. But it's a very Aristotelian argument, and I think there's a lot to it. So starting with A prime, mirroring Aristotle's A, number is a property of magnitude of pluralities. So again, the idea that number is ascribed to just a big plurality of things, okay? And then you have the second claim that for any plurality, it's possible to think of a larger plurality. How do you do that? Well, Aristotle thought it was really, really easy. Just add one thing. After contour, we know it's not quite that easy. When the collection is infinite, adding one thing does not result in a larger collection. But we have a different way of doing it. Remember Cantor's theorem as this powerful way of going from one collection to an even more numerous collection. So what we're going to do now is to apply a plural generalization of Cantor's theorem. Cantor's theorem talks about sets, but now I'm talking just about pluralities, about many, many objects, many ones, as Aristotle put it. And the generalization says that every plurality, assuming it consists of two or more objects, so it's a genuine plurality, has more subpluralities than it has members. Okay, so that is your powerful way of going beyond in size. So any plurality, no matter how large, no matter what kind of plurality, it's got more subpluralities than it has members. So you can transcend, you can go beyond that plurality in number. That's possible by this version of Cantor's theorem. So it follows then that absolute infinity is potential, never actual. The property of absolute infinity is ascribed not to an extension, as I prefer to put it, or to a plurality of ones, to echo Aristotle. That's not what absolute infinity is ascribed to. Rather, it's ascribed to an intention, what Aristotle talked about as a process of coming to be. I think process talk here is too temporal, so I'm not so happy with that, but an intention as opposed to an extension is my preferred way. But the point is still a very Aristotelian one, that when you look at the whole extended number line, the long number line with Aleph 0, Aleph 1, and so on it, that Cantor gave us, that's got to have the property of a pairon, because the extended number line is not a quantity or a plurality of ones, a plurality of numbers. Since if it were, by these considerations, you could go beyond that plurality in size. So the whole number line cannot be a plurality of ones, a plurality of numbers. It's more akin to a process or the intention of having ever larger numbers. So the claim here, a substantive claim, is that it's not enough to just talk with Cantor about absolute infinity. You need to understand that absolute infinity as a kind of a pairon. It needs to have that mode of being, or that mode of existence, since otherwise you could go beyond even absolute infinity, and absolute infinity wouldn't be absolute after all. So, third and final claim then that I want to make. I've anticipated this already, actually. So, a pairon sheds light on absolute infinity, because the mode of existence of the extended number line is a pairon. It's what Aristotle says is the mode of existence of a pairon. So the extended number line mustn't be seen as just a huge plurality of numbers. Rather, it's an intention or a concept, not quite a process, because that's too temporal, as mentioned. So it's an intention without a corresponding extension. And that's unfamiliar, right? We're used to, from elementary logic, to thinking that whenever you have an intention, there is a corresponding extension, all the things satisfying that intention. But not so in this case. And that is the core of Aristotle's view, as I understand it. So this also has a nice feature of explaining what would otherwise be a bit of a mystery about Cantorian doctrine concerning absolute infinity. So Cantor says that absolute infinity is absolute. It's unincreasable. You can't go beyond it. But then if absolute infinity is instantiated by a plurality, well, pluralities are increasable. You can go beyond pluralities in size by generalized Cantor's theorem. So to get absolute infinity as unincreasable, you really need to see it as a concept of surpassing every possible quantity. And when you see it in that way, so a pairon or absolute infinity is a property of surpassing every possible quantity, every possible plurality in size, then it's unincreasable because you have already taken into account every possible increase. Right? You have said that I'm interested in the property of going beyond every possible quantity. So you've used the whole modal dimension, as it were, for all it's worth. So by talking about the possibility of surpassing again, there's no further surpassing to be done. And that is why one cannot surpass absolute infinity. So by seeing absolute infinity in this kind of modernized Aristotelian way, you explain this feature of Cantor's view, which would otherwise be a mystery. Okay, to wrap up then. It's nice to write just the usual infinity sign for a pairon, surpassing every quantity. And then we saw that Cantor has two notions of infinity. So off the scale of natural numbers, off the scale of all numbers. So we really have three signs here. And now using that, I can give you a summary of the whole talk in just 3 characters. Infinity is, infinity or a pairon is identical with absolute infinity in the Cantorian sense. So that's it. Let me stop there. Thank you.
All right, thanks so much. That leaves us a full 15 minutes for questions. So just raise your hand on Zoom and I'll call on you. Yes, Remkes.
Hello, thank you. Thank you for inviting me or letting me be here via another invitation. Most of you don't know who I am. I'm a mathematician interested in Aristotle and philosophy. So I come from another perspective here.
Mhm.
Does this argument you've made basically apply to every proper class in say von Neumann-Bernays Gödel set theory?
The argument, let me see, you probably mean the
This absolute
argument for
infinity.
extending.
Yeah.
No, this is quite specific to pluralities as I see it. So when you have a plurality of things, then the Cantorian theorem applies, and it's possible to go beyond. So every plurality on this view can be surpassed in size, but not every class. So if you think of the class in a more intentional way, that it's say the class tied to the process of generating numbers or generating sets or whatever, then the class may well be one that you can go beyond. Does that help?
Yeah, I think so.
Yeah.
I mean, I'm thinking about going beyond as membership versus inclusion, the fact that we have subclasses, but classes cannot be members of other classes, and trying to fit like, is this actual infinity does that work for the Gödel constructible universe or the von Neumann hierarchy, or is it some larger notion of just everything that set theory?
Okay, good. So when you look at the property of absolute infinity in the Cantorian sense, so big omega, yeah, what are some examples of collections, loosely speaking, that are absolutely infinite? Yeah, so all of the sets would of course be one, all of the numbers, ordinal numbers, the whole extended number line. Also, the constructible hierarchy would have that property, as I see it.
Okay.
And I see all of these as permissible classes. You mentioned classes here.
Right.
So I think it makes sense to have these as classes. I'm fine with that. But these classes shouldn't be understood as just a plurality of ones or of objects. So they can't be seen as actual. So this is where Cantor talks about classes when the paradoxes had arisen. It talks about classes as inconsistent multiplicities. They can't all be present simultaneously. So that is a kind of view I take of these classes.
Okay, thank you. I think I understand.
Yeah, good, thanks.
All right, thanks. Andre?
Yeah, thank you, Øystein, very much. Just one short remark. I actually think the argument can be strengthened somehow because this reference to Cantor's theorem, it works only if we're talking about set theory like more than 100 years ago, right? And we are doing today's set theory, then of course inaccessible cardinals and so on. But still it looks like the argument works, right? All these new cardinals from Malot to Woodin kind of propose new way to extend this big omega. Yeah, and in that sense, indeed, it looks like very, very coherent idea to say it's potential in a sense. But I wonder, it's really, if we really take this point of view, which I think is very interesting again, it's kind of changed the usual perspective on potential versus actual infinity. Because say people normally say something like, okay, we don't want actual infinity, we want potential, but that comes back to the idea that after all, we accept only countable infinity, right? So after all, we may leave it technically up to you how you think it's potentially or actually, this is for philosophers, but technically only countable. But now it's really changes, right? If somehow we incorporate incorporate, all these high infinities, right? And big cardinals, including possibly even inaccessible cardinals, and still keeping the idea of potential infinity in that sense. So it's something different. So probably you could just suggest what kind of consequences, more mathematical, say for set series, this changing perspective could imply.
Yeah, thank you. So there's a lot there. Let me comment on two features of what you said. So yes, there are even stronger ways now of surpassing infinite collections. See if I can get my pen to work here. So I talked about this generalization of contrast theorem, and we have yet better ways too. This suffices to go beyond any plurality, so it suffices for my purposes. But of course, you're totally right. One can have even more powerful mechanisms to plug in here. The other thing I wanted to mention, which relates to the previous exchange too, is that this is a way of going beyond kind of an actual collection, to use Aristotelian terminology. So actual collections, or collections that are substance-like, they can be transcended. But collections that are process-like or merely potential, they cannot be gone beyond. So if you think of say, the hierarchy of all sets as kind of the process of forming ever more sets, then since that's thought of in intention, you can't go beyond it. So then any attempt to go beyond, then this intention of being a set will just follow along. So if you introduce more sets, then they too will fall under this concept V of being a set.
All right. I'm sorry, Andre, did you want to follow up quick?
No, it's okay. I just
to
think more about it. Thank you very much. Yes, thanks.
No, thanks for your question. All right, Martina, go ahead.
Yeah, again, thank you very much. I would like again to comment from an Aristotelian side. I am currently working on Aristotle's conception of the infinite, so I'm very invested in those questions. And I'd like to ask more about what is the evidence by which we prove that for Aristotle, every quantity is finite? Because in fact, there is some discussion in the literature about whether there is textual evidence available for this. Because Aristotle, in fact, claims that if there is something that is infinite, it must be some quantity in various parts of the physics. And again, for example, he defines number, and it seems to be a definition by genus and differentia as a definite plurality, Plato's Peperas Menon, which seems to imply that one can at least conceive a plurality, and since every plurality is a quantity that is infinite. So I'm still not clear. I haven't cleared my mind about whether these supposed infinite pluralities would exist in the Aristotelian universe, but I would discuss more about the question whether for Aristotle every quantity is by definition finite, and so I would like to ask more about this.
Good. So is every quantity by definition finite, according to Aristotle? Quite possibly not. I'm not enough of a scholar here to have a view, but for what it's worth, which is not a lot, I don't see why that should be so, why it should be kind of definitional that the quantities are finite. So what I proposed here, and I carefully avoided ascribing this response to Aristotle, I said that this is kind of seeing now, using what we now know to look back at what's going on here. And he's working with this Euclidean conception of quantities. Then you have quantities that got to be finite if you want the Archimedean principle. So that's a further commitment and not part of a definition. So I think I can agree with you that it's not definitional for Aristotle that quantities are finite. Quantities are what they are. They're kind of size properties of wholes, whatever the wholes are. And that's good. And then you can plug in from the side, as it were, this Archimedean principle, and you get this conclusion. And he probably did that, but that doesn't have to be definitional. And then also something cool happens if you're right, which you probably are. So remember this stuff that I said a pairon is closer to absolute infinity than to infinity. Okay, so absolute infinity is being off the scale of quantities, numbers altogether. Okay, so for this to really be an exciting claim, I kind of need, come to think of it, what you're saying, that it's not definitional for Aristotle that quantities are finite. Right, so here the claim is that in intension, this is the same as that. But then you plug in from the sideline again a view of what quantities are, which makes a pairon extensionally equivalent to our notion of infinity. So it's a very nice point. Maybe you could help me with some references for that. Just email me some references for the view you had in mind.
Yeah, sure. I can provide some articles that there are recent articles which it is argued also for the claim that Aristotle might counter actually infinite pluralities in his ontology. If, for example, the status of the single objects is its potential, that there is a kind of distinction between the actuality of the collection and the actuality as a property of existence of the object involved. So it is very difficult. I'm not still sure whether I agree with this view, but I think it's very interesting. So I would happily provide some reference.
Please do. And what you said about the distinction between actuality of the collection and actuality of its members is precisely what I want to say concerning proper classes in mathematics, like all the ordinals or all the sets, that these collections can exist, but all their members can't be actual simultaneously.
That's very, very interesting. Thanks.
All right, Stefan, if you just keep it quick, we have just a few minutes.
Yeah, so can you hear me?
Yeah.
Okay. Yeah, so I come from yet another background from computer science. So I'm a little bit maybe in a strange place here. But I was wondering, so you talk about Aristotelian philosophy, about mathematics, but there is this whole other side of computation, which is, and some of the things you talk about seem to be more about computation. And it's just a very general question. Has this sort of, have these sort of ideas ever been considered from the point of view of the modern findings of computer science? For instance, the Curry-Howard isomorphism, where you have basically language terms, and each language term is computed on. So these would be finite quantities in a sense. And then these language terms have types, and these types are mathematical objects, or can be given a meaning of mathematical objects. Do you know there is any literature trying to approach computation from an Aristotelian point of view?
I don't myself know of anything just off the cuff, but it does invite that kind of perspective, the Aristotelian view. So probably someone's thought about it. And what I have in mind when I say it invites that perspective is that you have this view that the infinite apeiron is kind of a process of coming to be. So something happens in a kind of quasi-temporal manner, and that's very computational in character. So kind of producing set after set, number after number. So there's something iterative, generative, and it is very natural to try to develop that in a computer science inspired way.
All right, thank you so much for Øystein for joining us, making the time. We really appreciate the talk, and so we'll be back in just 10 minutes, more or less exactly, for James Franklin's talk.